for inviting me to actually do some work, which I haven't done any so far. So, and yeah, anyways, thanks everybody for coming. And yeah, and it's gonna be great, even though maybe swimming in Jesus Green Lido is even more fun. But in the morning, we're gonna talk about core entropy. And by the way, in the afternoon at 4, there will be a little bit of mathematical theater that we're gonna play. So you're all invited, and we will do something different. What?
Isn't that compulsory?
Of course. Okay, so what about core entropy? So yeah, so core entropy, as you probably have heard before, is this concept that was basically introduced by Bill Thurston as one of the last projects of his life. So of course already it's been almost 14 years that he died, but you know, and in the last few years of his life was trying to give these lectures at Cornell and some other place, and sending emails to everybody in the math community to figure out some questions that he was interested in. And so in the later, 15 years, some people have tried to figure out what he actually meant and what can be proven and so far. So there's still more to be done, but this is certainly we've made a bit of progress for sure. So before we go into that, so core entropy is a notion of entropy for complex polynomial maps. Possibly could be extended to rational maps, but this really hasn't been done so much. But certainly for polynomial maps. And the first, of course, notion of entropy that we encounter in dynamics is topological entropy, say for real quadratic maps. So first, let's dive in a little bit into this concept of entropy for real maps. So of course, you might have seen such definition before when you have a continuous map of a compact house of space. And so there's various notions of entropy, of course. There is two basic ones. There's a measure theoretic notion, and there is a topological notion. Of course, they're very closely related. But before we even get into that, what is the general, very, very general notion of entropy? What is entropy about? Well, the idea is, because there's this formula, but what is the meaning of this formula? The way I think about it is the following. You have X, the space, and you want to perform some experiment. And the way the outcome of this experiment is that your set is partitioned into a bunch of subsets. So each subset corresponds to the outcome of your experiment. So you're measuring, say, the temperature, and there's like 6 possible temperatures that could occur. And so now the question is, what is the information that is encoded once you do this experiment? How much information do you get? So suppose that X is not, in the classical case, which is the one that comes from more like physical reality, like you have maybe a probability on X. And so you want to know how much information do I gain? Well, suppose that your outcomes are very unequal. Maybe there are some outcomes that are very, very unlikely, and some outcome which is super likely, like France wins the World Cup, or Capo Verde wins the World Cup. So if Capo Verde actually wins the World Cup, we do get a lot of information because it's a very rare event. And so that's why people introduce this information function, which is minus log of the measure of the piece of the partition. So basically, there's a partition. So X is, it's split into a bunch of pieces, which are given by the outcomes. And then you have the piece of the partition that X belongs to has some measure. And so this is why minus log, because when the probability is 1, the information that you gain is almost 0. And if this is very, very small, the information that you get goes to infinity. So this is one reason why you get log. Also, log has some convexity properties that are also very meaningful, but let's not do that. Okay, so that's the measure theoretic notion, and then the entropy of of this partition of this outcome with respect to this probability P. We all know that it's this average, which is so it's we can say is the expectation according to this measure of this information function. So usually you have p log p. So log p comes from the information function, and the p comes from the expectation. So that's the measure theoretic notion. But today we're not going to go too much into the measure theoretic notion, but just the topological notion, which is a little bit easier in many ways, because, well, there's two ways you can think about this. One is, okay, what if you can change weights in the space? Maybe there's different probabilities. But when is this entropy the highest? Well, the entropy is easy to check. It's the highest when the probability of every event is the same, right? So if p of ai is 1 over n for every I, well, then the entropy of this is just the log of the number of outcomes. And this does not depend on the measure. And that's the topological interpretation. And so if we want to define topological entropy for a map of a compact space, well, we do a similar thing, except instead of doing the, splitting things according to measure or partition, we have a cover. So we have the space, and we consider a cover. So it's more or less the same thing, but you can have overlaps. And then you can ask, well, how many of these elements in this cover are enough to cover the whole space? And this we call n of u. And then this is for one step. But now we also have a dynamical system, right? We have the map f from x to x. And so now the question is, if I have time, I can take, I can measure in which part of the partition I am today, and also tomorrow, and the day after tomorrow, and so forth. So if I give n possible days, I want to measure what are all the possibilities, the possible sequences of outcomes that I get. And so clearly, the more possibilities there are, the more the system is chaotic. So there's higher entropy. For instance, if everything converges to a fixed point, eventually, for instance, all possible trajectory will be in one in one set, which is the one that contains the fixed point. So there will be no exponential growth, and so the entropy would be 0, for instance. And in general, if every possible combination is possible, then you're going to have very, very high entropy. Okay, this is somewhat very classical, of course. Is there any questions so far? Yeah.
Of the cover, are there open sets?
Yeah, in this topological theory, yeah, it's an open cover. Yeah.
I seem to remember the word topological comes from the fact of two variants.
That's right. That's right. So in this, in fact, there are two properties that are probably important. So that the topological entropy of f to the n, as you would imagine, is n times the entropy of f. And then if two maps are conjugate, if f equals hg h inverse, which h is a homomorphism, then the topological entropy is the same. So there is no measure. Of course, there's also the variational principle that tells you that if you take the measurable entropy for all the invariant measures on a compact space, and you take the supremum of all those over all the invariant measures, then you do get, again, the topological. Okay, more questions? Okay, so now we go more deeply into closer to what we care about more, which is, for instance, quadratic polynomials. So for instance, for interval maps, there are other ways to compute the entropy. So one way to compute the entropy, which is due to Misiurewicz and Slank, is by counting laps. So what is a lap? So suppose we have a map of the interval that has finitely many pieces of monotonicity. So for instance, if you have a quadratic real polynomial, it has 2. Then you can iterate this map, and you count how many pieces of monotonicity there are. And so for instance, if you iterate this, you have 2 laps, you get 4 laps, then you get 8 laps, and then what's next. If you've seen these slides before, you should remember what's next. How many pieces?
16.
16 is at most, right? But actually, in this case, it's 14. So, yeah. And so forth. So, of course, this is expected to grow exponentially fast. And so you get this number. So this, of course, this definition has the merit that there is somewhat not super complicated to compute. And somehow the limit exists by just some subadditivity of the sequence, which is not so hard. However, of course, you have to do still a limiting process. So it's not super explicit. If I ask you, what is this number? Well, it's a limit. OK? So, and of course, also in terms of partitions, let's notice the following, that if we start with the first iterate, right, we have a natural partition, which is, you have a left side and a right side. So you have two. You record if you're either left or right, and then if you count the number of laps of the nth iterate, for instance, if I iterate 3 times, a lap of the third iterate means I record on which side I am at first step, and then I also record on which side I am at the second step, and on which side I am at the third step. So you get these sequences. The laps of Fn are exactly the sequences that are admissible for this set. So far, so good. OK. So now, on the other hand, suppose you have a map that is poscritically finite. So suppose that, for instance, you have a quadratic polynomial, and the orbit of the critical point is finite. For instance, it has period 3. So this is what, of course, the aficionados of the Mandelbrot set would recognize as the airplane map. So you have a map of period 3. So if you draw it in the interval, the dynamics just looks like that. If you draw the graph, it looks like that. And so we know that in this case, you have actually a Markov partition because you have an interval A and an interval B. And you can construct what are all the possible sequences of A's and B's by looking at one step and then doing it iteratively according to a matrix, right? So we can define a matrix here, since there are two pieces of this partition, and in this case, really f of A really is the union of A union B, and f of B really is A. And so we can construct a 2x2 matrix. In this case, you get this matrix, right? A, B, A, B. And then if you take powers of this matrix, so you want to count the number of laps, the number of sequences that start in A and end in A are going to be this one, and A and end in B and so forth. It will be this one and so forth. So you take powers of this. And so how fast do the powers of a matrix grow by the Perron-Frobenius theorem? Well, certainly if it's a primitive matrix, positive irreducible matrix, they grow like the leading eigenvalue. And in this case, it's not hard to compute. The leading eigenvalue is the golden mean, right? And by the way, this particular map has this property. This matrix you've probably seen before if you've taught linear algebra recently. It's a nice example, because this matrix also encodes the Fibonacci sequence, right? And so powers of this matrix gives you the Fibonacci sequence. So for this particular map, if you take the nth iterate and you take the number of laps, these are the Fibonacci numbers. And they grow exactly like the golden mean, as we all know. Right? Any other questions?
So these integers are actually long calculated.
Absolutely. This is exactly what I was going to say, exactly. For the algebraic, the arithmetic dynamicists in the audience, if you take, yeah, of course, there's always this issue about the log that we did before. So there's a lambda is the growth rate, which is an algebraic number, and then the log of the algebraic number would be the actual entropy. But of course, if you're interested in the algebraic properties of the system, you might just as well forget about the log and look at that. So yeah, this is a degree 2, of course, algebraic number, because there's 2 pieces in the partition, and then you can ask if there's 10 pieces of the partition, is the polynomial, minimal polynomial irreducible or not? This is actually a good question, which is not so trivial, actually. More questions? Okay, so now let's go to our favorite family, which is z squared plus c. And let's start with the real one. So you start with z squared plus c, where c is real. Now, this, of course, has a very, very long history, very nice, nice history that people looked at how the entropy changes as you change with the parameter c. So for each c, you have a dynamical system in the interval, and then you're going to have a number, which is the entropy. And so this is the famous function that was considered by many people, and in particular, this culminated in the famous work of Milner and Thurston, which showed that the entropy for real, what happened? This I should not have done. So probably not a big deal, but nope. Okay, well, it's not a big deal. So anyways, so this is the original picture from Milner and Thurston. What they did is they had a slightly different parameterization. So they had the so-called logistic family, which is at the end of the day is the same family, x times 1 minus x times, and a is the parameter instead of c. But this is conjugate to z squared plus c. The only difference is that in the a parameterization, as a increases, the entropy increases, while in the c parameterization, as c increases, the entropy decreases. I mean, usually we are used in complex dynamics to seeing pictures of the Mandelbrot set, we were going to see shortly. And in the pictures of the Mandelbrot set, when you do z squared plus c, the Mandelbrot set is oriented this way. Let's see. And so forth. And so you start from, from 1/4, and you go all the way to -2. As you go towards the tip of the Mandelbrot set, this corresponds to c decreasing, of course. And the entropy is increasing. So that's how it is, but it is continuous and monotone, even though it's not strictly monotone, is monotone in a weak sense, because there are plateaus for the entropy. And some plateaus are more obvious than others. So the plateaus corresponding to hyperbolic components, those are more or less obvious because the polynomials are basically almost conjugate to each other. I mean, they're very similar, except it's for the center. But anyways, the entropy really doesn't change. And still there are interesting things going on here. There's this fractal structure of this map that has been also studied. So this function, for instance, is definitely not smooth. And we're going to see a bit later what other things one could say about this. So this is somewhat the classical picture. And what we want to do in the theory of core entropy is to generalize this classical picture to the theory of complex polynomials. So at the moment, we have a map of a real interval, and we have an entropy because it's a compact metric space, and so everything can be computed. Now, for complex polynomials, there could be many things that one could do. And the easiest thing, of course, the first thing you comes to mind would be, you have a complex polynomial. Complex polynomial is a map of the Riemann sphere. And however, in this case, well, the answer is nice, but probably too nice for us. Because if you have a polynomial of degree d as a map of the Riemann sphere to itself, it has exactly entropy log d. So for quadratic, just log 2. So it's constant over parameter space. It's a very nice analytic function of parameter space, but it's constant. And the reason, for instance, if you want a heuristic reason here, is to say that, if I have a point defined over C, and I take its pre-images, well, there's always d of them and I do it twice, you get d squared and so forth, almost, except for, for the critical value. But basically, you have d to the n preimages, and so the growth rate of that would be the entropy, basically. So that doesn't really depend on C. Right, and that's because, again, this system is invariant forward and backward, while you see that the real system is different, because if I have a real point, I have a quadratic polynomial, I take the preimages of a real point. Well, there's two of them, but sometimes they're real, sometimes they're complex. And if they're complex, we don't count them in the original real theory. And so we use this fact that the real interval is forward invariant by a real polynomial, but it's not backward invariant necessarily. And so, and this will be very relevant to how to define for the complex. Okay? Yes?
I wanted to really, but is it easy to understand? I mean, it looks like the doubling bifurcation, for example, doesn't change this initially.
That's correct. That's exactly right. So if you do one bifurcation, the entropy indeed doesn't change. That's right. Yeah. So yeah, I can tell you more. I mean, this way we understand very well what happens to the combinatorics. But basically, yeah, just the length of every cycle doubles, but there's nothing else basically. And yeah, I can actually maybe I can tell you something about how to compute this that will maybe give it a little bit more of a flavor why this is the case. So we do understand very, very well what happens when you do bifurcations, but basically whenever we go to an adjacent hyperbolic component, the entropy doesn't change. So certainly for the whole cascade, it doesn't change. And in fact, the Feigenbaum point indeed is the first point where the entropy then becomes positive. So in a sense, really, the chaos starts after that in that sense. Okay. So, and also, so yeah, so how do we, maybe I also want to give you an idea on how to actually compute this entropy in the real case, which you probably have seen it in the paper of Milner and Thurston. But let me give you my take on it, because they have a very nice formula. And the question is, why is this formula true? So let me tell you what the way I see it, which I think is at least not what's written there. So can I just erase the swim first? I'm sorry about it. We can rewrite it. I think everybody.
I'm sure everyone has.
Everybody noticed. Yeah, exactly. So the famous way to compute entropy for real quadratic maps is this famous kneading theory. And the kneading theory really looks so simple that you can really wonder why it works, especially for quadratics. So at the end, so what is the kneading theory? So suppose we have a quadratic maps on an interval. Let's say that the critical point is at 0, for instance. Of course, it could be also a topological unimodal map, but anyways, it's the same. So we have, so the graph of the map, of course, looks somewhat like this. And then you have this critical point. And so we have a natural partition, which is either you're to the left or to the right of this critical point. And so we define a sine function, epsilon of x, which is just -1 if x is less than 0, and +1 if x is bigger than 0. And so this is -1, and this is +1. So why do we pick this sign? It's because it's the sign, basically, of the derivative. It's like this is decreasing, and this is increasing. And now we introduce a coding with respect to this partition. We can introduce the itinerary for f of a point x, which is basically just epsilon of x, epsilon of f of x, epsilon of f of n of x. So for the moment, I'm assuming that they never hit 0, but I'll show you there's a trick to figure out what is the correct sign. In some theories, people put a different symbol at 0, but I really don't like that, because I think there is a natural way to define it all over. But so okay, you have this, and then you define the needing sequence. So needing sequence. And so the needing sequence is something that depends only on the map, and it's basically, so let's say that this is f of x is x squared plus c, so c is the critical point, is critical value, sorry. So we take basically the itinerary of the critical value. Okay? And again, if this is not just critically finite, this is obvious. If it's pre-periodic, there are some times where you have to decide, but I'll show you how to decide it in an example. So for instance, let's do the example of the airplane map. So we have this map. So this is -1, this is +1. So if you start at C, of course, you first have, so kf, we start with -1 for sure. Then we go to the other side, we get +1. Then we have to decide. And the trick is that we take a limit in the following way. So for instance, if you start from the critical point, okay, you take a neighborhood of the critical point, and you map it through. So now it folds. So it folds, it becomes a one-sided neighborhood. So now the sign is well defined. And now it goes by homomorphism. So now it gets to this neighborhood. And now it's orientation preserving, it gets you to this neighborhood. So the correct sign here is -1. And so forth. So, okay, this is then it's periodic, like that. Because whenever you fold, then you don't have any choice anymore. And so that's the correct way. And then you do this extremely simple-minded thing, which is you construct this power series. So you construct the power series P of t, or let's say f of t, which is just the following. Okay, let's normalize it like this. You take, let's call this k1. Yeah, let's call this kn. And so we take k1, k2, kn, t to the n. So you take just the products of all the coefficients up to n, and you consider this. And so the crazy theorem of Milnor and Thurston is that this is how you compute the entropy. And the way is you consider the zeros of this power series. So this is a power series which has bounded coefficients because everything is plus minus 1. And this power series has the smallest, so this defines a holomorphic function in the disk, right? So PDF is holomorphic in the disk, and basically, so basically the entropy is the smallest zero in the following sense. So if lambda is let's say e to the minus h, then Pf of s is non-zero for s smaller than lambda. And well, if lambda is 1, well, this function just never vanishes. If in the disk, if lambda is smaller than 1, then it vanishes. So if the entropy is bigger than 0, then there is a root. And P f of lambda equal 0 if lambda is smaller. Okay, so this is the classical picture, like very similar to the zeta function pictures, of course, that you have, in fact, 1 over p is basically the zeta function. So there's a good relation there. And so there is a smallest root which happens to be real. And this is so beautiful because, well, first of all, it gives you a very practical way to compute it. And also, it tells you that if you change the coefficient a little bit, then the zeros, by, say, Rouché's theorem, the zeros of a holomorphic function will also change only by a little bit. So there would be continuity in this entropy. Of course, there's many things to check, but this is the case. So in fact, as an example, maybe for the airplane map, so we have k of f is this one. So for the airplane map, we see that if you track, you get 1, then you get minus t, then you get minus t squared, then you get plus t cubed. You take the cumulative products. So whenever you have a minus, you change sign. Whenever you have plus, you keep the sign. So you change, you get minus, you keep it, you get minus, you change, you get plus. And then what's next? Yeah, I think it is minus. And it should be again minus, and then it's plus again, and so forth. Okay?
What is this polynomial called?
Sorry?
You said something name. What is this polynomial called?
As the airplane.
I just need the P of T.
Yeah.
Oh, the kneading. Oh, this one is a kneading series or kneading polynomial. Kneading series.
It's about these.
Yeah, it's a power series. In this case, it becomes, there is a polynomial associated to it because the map is postcritically finite. So this sequence is periodic or eventually periodic. And in fact, in this case, well, you can guess what is the analytic formula because it's like you have 1 minus t minus t squared. Then you multiply everything by t cubed. You get 1 minus t minus t squared, and so forth. And so, in fact, in this case, it's a rational function. It's 1 minus t squared divided by 1 minus t cubed. Right? So this t cubed is because the period is 3. And so, but at the end of the day, the important roots are, so the smallest root here, yeah, so basically, yeah, lambda here is 1 over the golden mean, is 2 over square root of 5 plus 1. You just have to take the zeros of this polynomial, of course.
Can this be algebraic? Or does it have to be transcendental?
Right, so if the map is postcritically finite, again, it's going to be algebraic. Yeah, this is going to be a rational function.
Can it be algebraic but not rational?
Can it be algebraic but not rational? I'm inclined to say this is an open question, but I'm not so sure. But I think similar questions are quite open, like because there should be some very very non-trivial relation, and I'm not sure actually. Yeah. So yeah, and also so if you want to know what happens if you do the period doubling, just because Holly asked. So let me show you. We know pretty well what happens if you do the period doubling. For instance, if you have the airplane and you do the period doubling of the airplane, so remember you have a period 3 component, and then you have a period 6 component. So what happens if you do the doubling of the airplane here? At some point, you switch one of those, which I think in this case would be -1. +1, you switch on the other side, which is +1, and so forth. And then these ones are staying the same, and this one and this one doesn't change, I think. Or yeah, anyways, I think at the end of the day, when you do the cumulative thing, you get that P of, if you do the doubling of f, let's call it airplane 2. This is the doubling of the airplane. Well, this is almost it's almost the same, except there is an additional factor here. So you're gonna you're going to have something like this: 1 minus t squared, and then minus t cubed plus t fourth. Yeah, so you changed, you take the signs, you change the signs, you flip all the signs, and you change the product. Change 3 to 6. And so this is almost the same. It has almost the same roots because it's obtainable very easily from the previous one, right? Because this is just 1 minus t squared times 1 minus t cubed divided by 1 minus t to the 6. So when you do the doubling, the factor which is really important stays the same, and you only get the cyclotomic factors. And so you can have a very, very explicit way of studying the combinatorics of this real quadratic polynomials by the kneading theory. Yeah. And so, okay, now maybe. And so since I'm here, okay, I kind of wanted to still tell you the way I think about it, because I still think it's exciting. Since we're here at this point, I can tell you why is this formula true? Basically, why? So what you want to say is that why is the entropy at 0 of this object? So one way to go about it is to say that 1 over p is essentially the zeta function, and so the smallest 0 of the kneading polynomial or kneading series is the same as the smallest pole of the zeta function. So this is one way to go about it. Another way to go about it is to say the following: the idea is to look for a semi-conjugacy from F to a piecewise linear model with constant slope model. So basically a tent map P lambda. And because, okay, so first of all, you have to prove, which is some work, but not so hard, that if you have a tent map of slope lambda, so what is a tent map? Well, a tent map is a map that looks like this. It has two linear pieces, and for us, they have the same slope. So in fact, we're going to write some equation. We're going to say that T lambda of x is, we normalize it so that the critical point is at 0, and the critical value is at -1. This is just a normalization. So in this case, you get -1 plus epsilon, which is a sign, it's either plus or minus, lambda, which is the slope, times x. So this is the formula for the two branches. If epsilon is positive, you get this branch. Epsilon is negative, you get this branch. Okay? And so let's say that we know that the entropy of this tent map is what we want, is log lambda. Okay? And now, what is that we're trying to do? Well, let's say that we want to find a semi-conjugacy from our given unimodal map, semi-conjugacy phi, from our map F to there. It's not obvious that it exists, so, but and a semi-conjugacy that would preserve the entropy. Well, of course, so this is not obvious that it exists, but I think it's a good heuristic to see what you have to do. So because what is that you have to do? So you see that if phi is a semi-conjugacy, what you do, we start with a point x here in I, where, and you want to map it to some other point, let's say x prime in the domain of this map, right? So f x here, and well, what's the natural thing to do? Is, okay, you have the itinerary here with respect to this partition, and you have the itinerary here with respect to the other partition. So the natural thing to do is to say that the itinerary of this one goes to the itinerary of that one. So the itinerary of f of x should be the itinerary of, according to T lambda, of x prime. Okay? And this is easy to actually do, because T lambda is a very, very simple map. So let me tell you what happens here. So we can even do it. So suppose that this itinerary here is epsilon 1, epsilon 2, epsilon 3, so forth, epsilon n. So now what is the point x that has itinerary epsilon 1, epsilon 2, epsilon 3 according to T lambda? Okay? Well, let's try. So what it means that if I apply this map, I'm going to get this sequence. It means that, if you do T lambda n of x prime, yeah, let's call it xn, or x prime n. So what is it? Well, it means that you start with x prime, and you do T epsilon 1, then you do T epsilon 2, and you do T epsilon n. Where T epsilon is just, the version of this where you fix this epsilon. And these are linear maps. So we can invert this relation and say that x prime is what? That these are linear branches, so we already picked which branches. So we know that this is xn prime, T epsilon n minus 1, and so forth. T epsilon 2 minus 1. T epsilon 1. Now the T are expanding, the T inverse is contracting. So this is a good thing. And in fact, we can write it, because here we have the T, you see, T epsilon of x, as we said, is minus 1 plus epsilon lambda x. So if we call this y, we find that x is y plus 1 over epsilon lambda. Epsilon is plus or minus 1, so this is otherwise said is epsilon lambda inverse plus epsilon lambda inverse y. And then we can do the computation here, basically. So what is x prime? Well, you see, you have epsilon 1 lambda inverse plus epsilon 1 lambda inverse per times the second one, epsilon 2 lambda inverse plus epsilon 2 lambda inverse, and so forth. So this is epsilon 3 lambda inverse plus blah, blah, blah. And so at the end of the day, you get precisely this formula. You get epsilon 1 lambda inverse plus epsilon 1 epsilon 2 lambda minus 2 plus and so forth, plus epsilon 1 epsilon n lambda minus n plus epsilon 1 epsilon n lambda minus n xn prime. And xn prime has to be bounded if this works. So you get a formula for x prime. And what is the formula? It's what you want. Is this power series, and then there's one more trick. So you see, you get that x prime is the sum, as you take the limit, is the sum of epsilon 1 epsilon n lambda to the minus n. Okay. So we say that we better say that this has to be phi of x. And now the second idea. The second idea is phi maps the critical value to the critical value. It better do.
Yes.
Excuse me, what is x here in phi of x?
Yeah, so x was a point in I, and we tried to construct this conjugacy or semi-conjugacy from I to j. So I is the domain of f, and j is the domain of the 10 map.
This power series,
Yes.
it doesn't have x in
Oh yeah, well, everything depends on x here. Yeah, this coefficient. Yeah, very much. Yes, yes, yes. Yeah, everything depends on x. But now we pick our favorite point. What is our favorite point? The critical value. And so what is the critical value? Well, we want that phi of c is -1 for what for what we said. And so what does this mean? It means that the sum from 1 to infinity of epsilon1 of c up to epsilon n of c, lambda to the -n, equals -1. And this is, so you see, lambda was not specified yet. But once we say this, then this pins down what lambda must be, because you have to have the Milnor-Thurston relation, and well, you just put the -1 to the other side. So this normalization kind of is done so that the computation becomes easier. So this is another way of interpreting why the Milnor-Thurston needing theory works. Of course, so if you look at the paper, there's this nice combinatorial relations between which are very beautiful. But in some sense, this is also another way of thinking about it. And in fact, this is exactly what happens. That if you do the Milnor-Thurston needing theory, you get a semi-conjugacy from the unimodal map to a pieces linear model with constant slope. And this is not always a conjugacy. Sometimes, especially if you have a renormalization, if you have some invariant interval, this could get collapsed to points. But in any case, it does preserve the entropy. So for each entropy, there is pieces linear model. However, given a pieces linear model, there could be more. There are sometimes more than one quadratic polynomial that realizes that. But so the combinatorics, so the entropy and the combinatorics are two different things, and the entropy and the combinatorics and the analysis are also slightly different from each other. But it is true there exists a way to semi-conjugate any unimodal map to pieces linear model, and this is very closely related to the Milnor-Thurston order. Maybe it's a very good time for questions. Yes. Yeah, yes, that's a very good question. Yeah, I'm not sure it comes directly from this argument. I mean, the point is that at the end of the day, you have some function that has all positive coefficients, and so if you look for the smallest, if you do 1 over it, you get that the smallest pole has to be real, because the function gets, if you compare two values, one that is positive real and one that is the same modulus, the real one has to be, at the real one, the function has to be bigger. So the smallest pole has to be real. So that's a separate argument that doesn't directly come from this. Yeah. So I'm not sure this is actually a proof or not, but this is certainly a way to think about it. Should be turnable into proof, but this is never written this in paper. More questions?
You should never use it like this for plus, right?
No, this is for every unimodal map. Yes, that's right. Okay, so this is what happens for reals. Of course, now we don't have too much time, but certainly I will tell you a few things of how to extend it to the complex world, if this works. Okay. So as I said, the problem is you cannot just take the map on the Riemann sphere. This is way too simple-minded. So you need to find a set which is invariant by the dynamics. It's forward invariant, but not backward invariant. Okay, so this is just a standard complex dynamics definitions. You have the Mandelbrot set, of course, and you know that you can uniformize the exterior of the Mandelbrot set using external rays. So let's go a little bit fast over this, since it's not even so useful at the moment. And then, of course, you know that conjecturally for every angle, there would be a ray on this side on the exterior of the Mandelbrot set, and conjecturally all the rays land. But of course, we don't know that yet. So there's always this tension about the combinatorics, the combinatorial model and the analytic model. And to be honest, the entropy theory is very much combinatorial. I mean, I don't think it could be really used to prove MLC or something, unfortunately. But at least but things are more cleaner on the. And of course, we know that rational rays land, conjecture, and yeah, this we know, and then conjecturally all the rays land, and so forth. So, but okay, let's gloss over this a little bit. So, what is the set that we're going to look at to define this core entropy? So, and the answer is the Hubbard tree. So, what is the Hubbard tree? So, the idea is that the Giulio set contains a sort of tree inside it. At least in the case where the Giulio set is connected and locally connected, which is the case we certainly start with. Certainly, if it's postcritically finite, it's even more true. So the idea is that, okay, you have your Giulio set, and then there is a notion of allowable arcs, which means that, you know, if I pick 2 points, x and y, this Giulio set is connected and locally connected, so it's path connected. So there is a path connecting them, which stays inside the filled Giulio set. So we denote it by x, y, k. And also it has a little bit of a rule to decide what happens in the Fatou components, because in the Fatou components, a priori you have a bit of more freedom. So the correct way to do it would be to say in a Fatou component you uniformize it and you go along internal rays. But this is not so essential for the entropy theory, but it's how to make sure that it's defined. And so every time I have some finite number of points in a Giulio set, I can connect them through this tree-like structure, which for instance, we could call it the allowable Hall. So you would have. And the Hubbard tree is just basically the allowable Hall of the postcritical orbit. So you see, in this case, you start with the critical point. You take all the forward images. So for instance, in this case, there's 4 of them, because it's postcritically finite. And then there is a canonical way to connect them. And it forms a tree-like structure. So of course, when we talk about Hubbard trees, you can think of them either as subset of the complex plane or just abstractly as trees, right? You can sort of abstract and then sometimes and with mark points. So of course, this is basically all you need if you want to say just compute the entropy. But of course, this also is an object that lives inside the complex plane, and you could ask other questions about that. And yeah, this is a forward invariant, but not backward invariant subset. So you see this orange arrows are the dynamics. And so you see that since the postcritical set by definition is forward invariant, you take this convex Hall, so to speak, and it's still forward invariant. But there's no, of course, if you take backward iterates, you're gonna get more and more branches. It's going to get bigger and bigger, and in the limit, it's going to converge to the whole Giulio set. And so, but we don't want to do that. That's the whole point. And so, the definition of Bill Thurston was that once you have this object, you do in fact construct. You can compute the core entropy, which is just the entropy of the restriction of this polynomial to this tree. So, given every polynomial nice enough, you have this tree inside. And by the way, yeah, it depends what you want. So if we are in this generality, the tree could have infinitely many branches. It could, if it was critically finite, no. And also, there are many other cases in which the tree has only finitely many branches, even though the map is not critically finite. But in general, well, it could have infinitely many branches. That definitely is the case. Anyways, you can define the entropy of this restriction. And so, for instance,
Can I discuss something about that?
sorry?
You include in the definition the assumption that the Giulio set is locally connected. Is it necessary for like defining the Hubbard or
Well, yeah, I think the way I think about it is that exactly. It's a I want the Giulio set to be path connected to define the Hubbard tree. That's mostly what I care about. Of course, you could define everything, for instance, in terms of laminations, and then you wouldn't need to assume any local connectivity. Yeah.
On the class, when we define an allowable R,
Yeah.
should we say that with intersection union of each but two component, is
Yeah.
the union of the internal race, or is intersection with the closure of each but two component? Because otherwise it seems like we wouldn't have uniqueness.
Yeah, with the closure. Yeah. No. Yeah, that's right. So so for the analytical theory, you kind of want the local connectivity, but then at the end of the day, all this can be purely defined sort of combinatorially in terms of laminations, and the tree is basically dual to this lamination. So yeah, which is something I do like very much, but I know. Yeah. Okay, and so let's just finish by giving some very basics about this. So okay, for instance, first example would be like if you have a tree like this, you have how to compute it. Well, there's one way to compute it, which is to really take the Markov partition again if you have a postcritically finite map. And then in this case, you would have four intervals. And then so you can still construct a matrix 4 by 4. And then again, here you have a leading eigenvalue. And then you can compute the entropy. So of course, this is still possible. However, much like in this real needing theory case, the problem is what happens if I perturb the parameter a little bit, because the big question that Thurston also put at some point, and there's all this banter between various people whether this is true or not, that if there's some continuity of this entropy. And so the point is that if we want to have a handle on any form of continuity, this is really not very good, because if I have a parameter that has tree like this and I perturb it a little bit, I immediately can branch off and get some parameter which is like this, and I can get infinitely many more complicated things and so forth. This is very easy to get if you perturb off of the vein. And so you would get a huge matrix, and then you cannot really control. And so that's why what we want to do with is to construct some analog to this Thurston needing theory for this core entropy case. And so that's what I did at some point. So I don't have time to describe everything, unfortunately. But in any case, let me show at least what are the various pictures. So the question of Thurston, or at least the pictures that he was showing many people, is this picture of the entropy as a function of the external rays in the Mandelbrot set. So basically, if you have an angle between 0 and multiple, between 0 and 2 pi, but if you look at it in multiple of 2 pi, it's like between 0 and 1. So you can produce a ray. So for every angle theta, you can look at the ray of angle theta and see where it lands. Let's say if it's rational, we certainly know it lands, and it determines a postcritically finite map f theta parameter here, and this guy will have some entropy. And so then you want to know this function. What is the function from theta, which is an angle in R mod z, to the entropy of f theta on its Hubbard tree? So this is a number. And so this is what happens, that this is the function. And so one question was this continuity and what happens about this picture. So first of all, obviously there's a symmetry here, which is very apparent, which has to do with just the z bar conjugation, because it's basically from here you start at 0. 0 is in the cusp of the Mandelbrot set, the entropy is 0. And then as you go along these famous elephants, the entropy goes up like that. And then it goes all the way up there at 1/2, which means is the tip of the Mandelbrot set, where the entropy is the highest, which is log 2. And OK, then you go the same. But then there are many things. Yeah, all this ups and downs. Well, these ups and downs are related to the structure of the Mandelbrot sets. So basically, two things are true. So one thing which is true is that there is monotonicity. It still holds here. So what does it mean to be monotone here? Sorry. Basically, it means that if you go from the center of the Mandelbrot set to a tip, so I have an arc here which I call a vein, and there is an order, there's a partial order of quadratic polynomials induced by the fact that, if you have let's say that theta 1 is here, lands here, and theta 2 lands here. So this one is smaller than this one because it's closer to the main cardioid. So you think of a dual tree in the Mandelbrot set, and so this induces an ordering. And so there is a monotonicity of entropy in the complex Mandelbrot set by saying that according to this ordering, if you get further from the main cardioid, this is a partial order, but still, the entropy can only go up. And then the other one is also related to the continuity. There are many, many other things, but let me just finish with this. So one thing that eventually we were able to prove, and in kind of two different ways, me and Duke and Schleicher, is that the core entropy does indeed extend to a function which is continuous on the whole circle. So as we were saying, a priori, we start with this function only defined on Q mod Z, so only on rational angles, because this gives you the postcritically finite polynomials. And then, a priori, it's unclear how to extend it. And then using an general, the whole idea is to define some sort of power series like this, which I explained many more times than this one, so that's why I wanted to do this one. So then you do indeed have a notion of entropy as a zero certain power series for every theta, including the irrational ones. And then for irrational ones, and then you can prove by the fact that if you move the coefficients a little bit, the zeros also move continuously. Then you can prove this continuity. Let me tell you one last thing, which is even more remarkable, I think, about this picture, which is I like the most, is that the regularity of this picture changes and in a very, very interesting way. So if the entropy is 0, the function is locally is continuous everywhere where the entropy is 0, but it's not Hölder continuous in a neighborhood of where it's 0. So it spikes up very fast near all these generalized Feigenbaum points. By the way, the 0 set has been proved by Low and Park that is just the main molecule. So you do all these bifurcations as many times as you want, but that's it. But the Hölder exponent gets better and better. The function is, if the entropy becomes positive, the function becomes Hölder locally. And in fact, okay, this has been claimed a few times, and I proved some of it, and Schleicher and students also have proved some other part of it. But at the end of the day, this certainly is true, is that once you take a point at certain height, and you look at the neighborhood, you look at the local Hölder exponent of the function here, and this is equal to the value of the function at that point. Well, divided by log 2. So I can, well, I don't think I want to skip all this, just show you the formula, but it's the same formula. Yeah, this is all the stuff that I'm not going to show you, but the punchline, which I think is quite a nice punchline, is this one. So yeah, so basically you have this formula, and then it took some time to prove it in full generality. Also, Wolf-Jung is part of it. But anyways, the point is, if you look at the entropy, and if you look at the local Hölder exponent of this function, this equal to the value of the function divided by log 2. So this function literally gets more and more regular as it gets higher. So the intuitive idea is that if I have a system with high entropy, and I perturb it, it's much harder to create even more entropy. rather than if I have a system with 0 entropy and I perturb it, somehow it seems much easier to create, for instance, you create more horseshoes and they have positive entropy. And this function is never Lipschitz, except at the tip. Well, it's never smooth, except at the tip it becomes, yeah, it becomes almost Lipschitz. It becomes Hölder with exponent 1 minus epsilon. So it's like at the very tip. I think it's differentiable at the tip, but that's what it is. Okay, I definitely ran out of time. Thank you for your attention. So.
Another final question for you. When it comes slide by alpha, do you mean as possible?
Yeah, that's right. So it's not just a lower bound. It's not just like, yeah, one bound is like to say that this is Hölder of this exponent. No, it's really the best possible. In a neighborhood, yeah. It's not the punctual pointwise estimate yet. Maybe it's also true for the pointwise estimate, but let's say that if you want the best exponent in a neighborhood, this is the best exponent.
One silly question for, on the bottom of this is like a non-recurrent for the doubling map, is that not just like rational?
No, rational would mean finite for the doubling map. No, it doesn't recur to the original point, I think. It has accumulation. It has to have accumulation points, right?
Well, if it's rational and you think the doubling map, and it does like a whole unit.
Well, it's not dense, the orbit, right? Not all the orbits are dense, right?
I mean, irrational or non,
I don't think so. It depends, you look at this infinite binary sequence and what are all the subsequences. You can easily create sequences that never contain 4 consecutive zeros, for instance.
Why aren't you just doing like Z squared?
Yeah, Z square.
Okay, so if you take an irrational angle and you apply Z squared,
Yeah.
right, and you're saying that you're requiring that 0 is, or sorry, 1 is.
I'm saying just that no, it's not always true that the orbit is dense. This is the first step.
Oh, sorry, you're taking Z squared and not like rotation by
No, it's not rotation. It's angle doubling. Exactly.
theta. Thank you.
Yeah, exactly. It's not an irrational rotation by theta, but it's an irrational angle, and you take angle doubling. So this is the shift on 2 symbols. Yeah, that's right.
And then my less than research question. You mentioned the result that the core entropy is 0 if and only if you're on the main node. So
That's right.
is the analysis result in place for the small copies of the Mandelbrot set that you take as minimal possible value?
Well, yes. I mean, I don't know how much of it is literally proven. I mean, I think whatever you have for the main, I'm pretty sure that given the main molecule, then if you just go to, if you just tune everything with something, then certainly you're still gonna have this region where it's constant. This is definitely the case. I mean, a priori, well, I think it's most definitely true, but I don't know if it's written anywhere because, when you go to a small copy, you have even more branches that don't come from. No, definitely should be true, but it's not completely obvious, I guess. Yeah.
You get like a block matrix for your Markov matrix, and then you just see that the renormalization is killed. Like, the eigenvalue has to be smaller.
Yeah, but this is not in one part, right?
And similarly, I mean, is there any explicit relationship between core entropy on the molecule versus the width of the angles? And
Well, it's not so obvious. Of course, the bigger weights have higher core entropy. I mean, this is almost true. I mean, but we don't have like, I don't know, Yoko's type inequality or something. Maybe there should be. I mean, it's not such a, maybe there would be, but I haven't thought about it. Yeah.
Can you define the cognate entropy on the integral case?
Yes, for sure. Yes, in fact, this we did. So yeah, so if you have a non-unicritical case, as long as you have a finite Hubbard tree, you can take the entropy, and then of course you have a parameter space which is bigger. So for instance, for cubics, you have two you know, you have two leaves that correspond to the two critical points. So the space is the parameter space is more complicated, but yes, and in fact we prove continuity in any degree.
Like for example, for slices.
Yeah. For slices, indeed. Well, if you have continuity on the whole parameter space, you also have it on the slice. But then there are nice questions. For instance, what are the maxima on the slices? I mean, I do have more pictures for the cubics, yeah, you have nice pictures for the slices. For instance, this is the cubic global, the cubic parameter space. So you have two parameters. So you have a surface, so to speak. But now you can have interesting slices. For instance, this is a unicritical slice. Yeah. So by the way, now we know that the set of maxima here is actually a Cantor set. So this is more interesting. This is a work by my student Jacob Cure. And then then you have other slices where you have only finitely many maxima. So yeah, it's very interesting to study what happens on all this stratum. I mean, and there's more to be said for sure. Yeah.